What is control engineering? Well, a quick way to answer that question is to open your webpage to Wikipedia, where it defines control engineering as TLDR. Okay, basically what control engineering is can be illustrated through this simple diagram. First of all, you need a system, and then an input and an output. These three basic components are what control engineering is all about, and there are tons of examples in everyday life to show this. A light bulb is a system whose input is a switch and whose output is light. A sprinkler is a system whose input is a faucet and whose output is water sprinkled over a large area. A dishwasher is a system whose input is a timer and whose output are clean dishes. So if control engineering can be demonstrated through these simple examples, then what makes it so complicated that Wikipedia has a long article for it, and that engineers spend so much time studying it, even earning PhDs in control engineering? To answer that question, we need to dig deeper by defining two types of control systems: an open-loop system and a closed-loop system. An open-loop system is a system where the input does not depend on the output. Take for example the dishwasher. If you set the timer to 1 minute, then the dishwasher will run for 1 minute regardless of what you place in it. If you place a whole cake there, the dishwasher will run for just 1 minute and you won't get a clean plate, just a soggy mess. Conversely, if you place clean plates in the dishwasher and run it, it will still run for 1 minute despite the fact that the plates are already clean. I hope you can see the problem with open loop systems now. The output can either be the desired output, but it can also be a complete mess. Not to mention, open loop systems also have no control over how much resources they waste, just like the dishwasher running even if the plates are already clean. The sprinkler system is another good example of an open loop system. If you turn on the sprinkler, it will sprinkle water all around its specified area, regardless if it's raining or not. Again, without the ability to relay information back to the input, open loop systems are prone to all sorts of situations where resources are wasted. For open loop systems to work optimally, a smart human being must always be there to check the output and adjust the input manually. Now, in contrast to the open loop system is the closed loop system. Closed loop systems are a little bit more complex, and they operate by having their input dependent on their output. The diagram shown earlier can be modified to show you exactly how closed loop systems operate. The output is not just left alone. It's connected to a sensor which measures the output. The sensor is then connected to a controller. The controller takes the actual output and compares it with the desired output. It computes for an error percentage and alters the input so that the actual output will always approach the desired output. These two parts, the sensor and controller, basically remove the human aspect of an optimized open-loop system and closes the loop completely with no human interaction. Let's go back to the dishwasher and pretend that there's this sensor which measures cleanliness. Every time you turn on the dishwasher, the cleanliness sensor constantly relays information to the controller, which adjusts the timer accordingly. If the time was set too long, then the controller shortens it. If the time was initially set too short, then the controller extends it. With the sensor and controller set in place, closed-loop systems manage resources much better. They also present an actual output that's always going to be closer to the desired output over time. The same thing can be said for a closed-loop sprinkler system. If a moisture sensor were set in the ground, that could serve as the basis for when the sprinkler system would run. If it was raining and the moisture level was high, then the sprinkler system could remain off. But if there was a drought and the moisture level was low, then the sprinkler system could automatically activate. Yes, automatically. If you still don't get the difference between the two, then this analogy might help. Let's say you're a student in a classroom with a professor who's teaching you control engineering. He teaches the required lessons for the day and the class ends with absolutely no interaction at all. This goes on for the rest of the semester with no questions, no quizzes, no seat works, and no final exams. This might sound like a dream until you get a job and your first task is to create a control system for the company. This is exactly what an open loop system is. The professor can teach you his best, but without any way of measuring, there's no telling what the output would be. You could learn everything about control engineering, but you could also be completely clueless about what your professor is teaching. Contrast that with a regular class, where questions, quizzes, seat works, and final exams exist. These things become the sensor in the system. They help gauge the learning depth of the students, and with this data, the professor can compare the actual output with the desired output and alter his teaching methods to try to minimize that gap. This is the perfect example of a closed system where the actual output is always approaching the desired output. The reality is, closed-loop systems are much preferred over open-loop systems in almost every scenario. But if I ask you to name 10 examples of real-world closed-loop system, chances are you won't get very far. This is because closed-loop systems are much more harder to create and thus they are more rare. But that doesn't mean that we should just sit down and do nothing. Creating more closed-loop systems will allow us to manage our resources much better. And in a world where lots and lots of commodities are being consumed at an insane rate, it's pretty important that we work towards a day where everything can be optimized. And that indeed is a day to look forward to.